Welcome, my dear students, to this next session on industrial metallurgy. This happens to be session number 30, and here I show the different topics that we would try to cover in this particular session. Uh, see, uh, in one of our earlier online sessions, we had discussed that whenever any equilibrium diagram is constructed, generally it is constructed making use of one or more experimental methods. And when you are making use of experimental techniques to create or generate something, there is always a possibility that you might have made some errors during the time of experiments, or during the time of data collection, or maybe during the time of construction, or maybe during the time of interpretation, etc., etc. So because these equilibrium diagrams that we have been drawing are being largely drawn through experimental data, it becomes important that we check the correctness of such diagrams. So today I'm going to discuss with you that if you have a binary equilibrium diagram with you, constructed through some experimental methods, and now you are interested in finding out whether the diagram is absolutely correct or not, this is how we go about it. As we have done for unary systems also, generally the accuracy of the diagrams is checked that we go to each type of region. For example, in this copper nickel binary equilibrium diagram, we have three distinct type of phase regions. We have two single phase regions. One single phase region is above the liquidus line, where we have liquid solution. Then we have another single phase region below the solidus line, where again we have single phase region, solid solution of copper and nickel. And third is this intermediate region where we have two phases, a mixture of liquid solution and solid solution. Now we have discussed that generally the accuracy of an equilibrium diagram is checked through the Gibbs phase rule. And how do we do it? We go to every region, and first we ask the diagram that when our material system is in this particular region, what do you say, how many degrees of freedom are available with the material system? And then for the same, so we get the answer to the degrees of freedom, and then we apply the Gibbs phase rule in the same region, and again we seek the answer from that equation: P plus F is equal to C plus 1. C plus 1 because for binary alloys pressure is fixed at 1 atmospheric, and we use the condensed Gibbs phase rule. And now from that condensed phase Gibbs phase rule, we ask the answer to the degrees of freedom. There must be parity in the answer of the degrees of freedom which comes for this region from the diagram, and then from the Gibbs phase rule applied to this region. Same we do for this region, same we do for this region. And in all types of phase regions, if the answers that are coming for the degrees of freedom from the diagram and then from the Gibbs phase rule applied to that region of the diagram, if there is complete parity, there is absolutely no problem with the diagram. But if you get even a single instance, even a single phase region where the answer to the degrees of freedom coming from the diagram is different from that coming from the Gibbs phase rule, the entire diagram needs to be relooked into and it has to be modified. It's wrong, right? Again, mind it, it's not that it is wrong in that particular area only where this disparity has come. The diagram might be wrong at any place. You need to relook it in its entirety. Now let us see how do we actually take from the diagram for any phase region that how many degrees of freedom are there with you. So students, for example, who are the candidates to become degrees of freedom in a two-phase diagram? It's either the temperature or the composition. And when I say composition, mind it, it would be composition of the existing phases. So we have to see for two things, whether for any given condition they are acting as a degree of freedom or not. One of them is temperature, the other is a composition. At the max we can have 2 degrees of freedom when both temperature and the composition will qualify to be called as a degree of freedom, or we can have one when either of these would qualify to be a degree of freedom, and in the worst case we'll have 0 degrees of freedom. how do we check whether temperature is a degree of freedom? You go to any region. For example, my material system is defined by the temperature composition point X, when it is at temperature Tx and has composition 16% nickel. How do I see how many degrees of freedom are with the material system when the system is at state X? What do we do? First, we'll check whether temperature is a degree of freedom or not. How do I check it? Please see, can I change the value of temperature from Tx to any other point? Still that uh, still the phases that were existing continue to exist. See students, what was the phase existing in the material system when it was at point X? It was only one phase. And what was the type of the phase? Liquid solution. So now if I have to check whether temperature is a degree of freedom or not, what I have to do, I have to see whether I can disturb this existing value of Tx and I can come to a newer temperature value, so that still this single liquid solution continues to exist in the system. And you can see, yes, you can disturb the value of Tx to this value or to this value, means you can disturb the value. And when you even come to this value, say see this newer value of temperature, still, so temperature is a degree of freedom over here. Then we have to check whether composition is a degree of freedom or not. And now I said, please remember, for composition means whether composition of the existing phases is a degree of freedom or not. So how do we check? Again move along this vertical line, again change the value of temperature. And see, for temperature we had seen whether with change in temperature the phase number and type is changing. If it is not changing, temperature is an independent variable and is a degree of freedom. Now, how do we check composition is a degree of freedom or not? We just have to check whether composition of the existing phases is dependent on the temperature value. If composition of the existing phases is dependent on the temperature value, then it's not an independent variable. Then composition is not a degree of freedom. But if you see that even on disturbing the value of temperature from the existing value, this Tx, if I see that existing phases continue to have same composition, then the composition of the phases is not dependent on the temperature of the material system, and hence it is also a degree of freedom. So students, when I was at point X at temperature Tx, and I've taken an alloy of 16% nickel, if liquid solution is existing in it, because it's a single phase is existing in it, the chemical composition of the phase is the same as is the chemical composition of the alloy system. So when I am at temperature Tx, there is only one phase liquid solution in the system. What is the chemical composition of that liquid solution? It's 16% nickel. Even when I change the value of temperature and I go to a higher temperature, you see still same liquid solution is existing and still its chemical composition is 16%. So composition does not remain dependent on temperature. So it is also a degree of freedom. So for any single phase region like this, or for a single phase region like this, this diagram is saying that there are 2 degrees of freedom. This is what the diagram is saying. Now we need to apply the Gibbs phase rule to this single phase region and find out whether the Gibbs phase rule also gives me that there are only 2 degrees of freedom. So let us see. This is what I have already discussed with you. Now when I apply, so these are the 3 different types of phase regions where checking has to be done, right? And I also explained how do we check this. And okay, so let's now see that as the Gibbs phase rule is applied. So students, if you apply the Gibbs phase rule over here sorry, here, if you apply the Gibbs phase rule over here, F will always come out to be 2. P plus F is equal to C plus 1. C, this is a 2-phase system, so right hand side becomes 3, and P plus F, P is 1, so F comes out to be 3 minus 1, 2. The same thing had come from the diagram. Now students, come to this temperature when the material system is defined by the temperature composition point Y. So when the temperature and composition is such that we are at point Y, there are 2 phases existing in the system, liquid and solid. Now again, let us see that how many number of degrees of freedom are there in this region. What does the diagram say? The diagram says, sir, you are at point Y. At this point, there are two phases existing: liquid solution of this composition and solid solution of this composition. So students, first let's check whether temperature is a degree of freedom or not. And how do we come to know whether temperature is a degree of freedom or not? Can I change the value of temperature from this existing value Ty, so that when I change the value of temperature, the phases do not change, they remain the same? I see that I can disturb the value of temperature from Ty to a newer value, and still I see that the same phases are existing. So temperature is a degree of freedom. But how do I check for composition? You have to see that at this temperature Ty, the phases that were existing were having chemical composition this. Even if I change the temperature, do they continue to show the same chemical composition? If they do not, then this means their composition is dependent on temperature. So if I come from point Y to a newer point like this, and now the tie line would be this. So still the phases are the same with change in temperature. That is, temperature is a degree of freedom. But no sooner I change the temperature, the chemical composition of the existing phases changes. That means composition is dependent on temperature. There is only one degree of freedom when for a binary alloy I am in a two-phase region. So degree of freedom is 1. When you apply the Gibbs phase rule over here, P plus F, C plus 1, P is 2, F will come out to be 1. So there is complete parity between the F results which are coming from the diagram and which are coming from the Gibbs phase rule. So this diagram for every region is obeying the Gibbs phase rule, and the diagram is absolutely correct. But students, if you try to apply the same to any equilibrium diagram which belongs to the type 2 system, see, the experimental method had given us that this is our diagram. So in this region there would not be any disparity. Here there would be no disparity. Here also there might not be any disparity. But when you will come to this region, okay, here also there might be disparity. But let me check here. See, when you are here, what is the diagram telling you? The diagram is telling you that suppose if you are over here, with change in temperature, existing phases would not change. So that means temperature is a degree of freedom. But then it says that if you, from an existing temperature, if you go to a newer temperature, for every different temperature, the existing phases do not change their chemical composition. Their chemical composition, irrespective of the temperature value, is always 100% bismuth and 100% cadmium. So how many degrees of freedom? 2 degrees of freedom. Temperature is a degree of freedom because with change in temperature in this region, phases are not changing. Composition is a degree of freedom because with change in temperature, the chemical composition of the existing phases is not changing. So that means both temperature as well as composition is a degree of freedom. But students, when you will apply the Gibbs phase rule over here, P plus F is equal to C plus 1. C is 2. So C plus 1 becomes 3. P plus F, we are in a two-phase region. So when you are in a two-phase region, P is 2 plus F. So P 2 plus F is 3. So F comes out to be 1. The Gibbs phase rule says that, mind you, F in this region must be 1, whereas your diagram is showing it to be 2. There is something wrong with your diagram. So here also the Gibbs phase rule would be beaten. Here also the Gibbs phase rule would be violated. So even if you were getting this disobedience of the Gibbs phase rule in any one region, the diagram was absolutely wrong, and you need to relook where you have made the blunder. So students, when we went back and we saw that we had made an assumption that there are two elements who are very different, but they are still showing 100% liquid solubility. Now the point is that these systems might be disobeying the Hume-Rothery rules for the formation of solid solutions to an extent. But if these are showing 100% liquid solubility, that's a great thing. They cannot show, they can show less solid solubility, but they cannot show zero solid solubility. And when repeated experiments were done and metallurgically the microstructures were observed, it was seen that they do not, as we assume that they separate out into pure bismuth and pure cadmium. It was wrong. They were showing some solid solubility, and pure metals were not solidifying. It was rather solid solutions which were solidifying. Yes, in the solid solution, the solubility of the solute was very, very less, that for all practical purposes it could be assumed to be zero. But solid solubility theoretically actually was not zero, it was to some an extent. So when you say that I am precipitating, so for a hypoeutectic alloy, so for a eutectic alloy, your assumption that liquid transforms via the eutectic reaction into bismuth and cadmium, no, it transforms to solid solution of bismuth as the solvent and another solid solution with cadmium as the solvent, but this solid solution was containing some amount of cadmium in it. And here the solid solution of cadmium as the solvent was not only cadmium, was containing some amount of bismuth in it. So rather it was not bismuth plus cadmium, it was alpha solid solution and beta solid solution. What was alpha solid solution? Solid solution of bismuth with cadmium as the solute. And what was beta solid solution? Solid solution with cadmium as the solvent, but bismuth has the solute in it. So when we revisited this diagram, there was a change in it, that here we are forming to some an extent very, very limited solid solubility, but in this entire triangular region we are getting a single phase region called alpha, solid solution of cadmium in bismuth. Cadmium is the solute, bismuth is the solvent. And on the extreme right, again we are getting a single phase region, a very small region with very, very limited solid solubility. And this is a region where we have beta solid solution. Bismuth is now the solute and cadmium is the solvent. So here we do not have liquid plus bismuth, rather we have liquid from this side and alpha from this side. So this region is containing liquid plus alpha, this region is containing liquid plus beta, this region is containing alpha plus beta. So this is the modified and the corrected diagram. And students, now again let us apply the Gibbs phase rule over here to check the validity of this diagram. You'll say, when you'll see, suppose you were at this temperature, if you change the temperature, you can disturb the value of existing temperature and still same type of and number of phases exist. So temperature is a degree of freedom. But suppose when you were here, phases existing were alpha and beta, but alpha had this chemical composition, beta had this chemical composition. No sooner now you disturb the value of temperature, alpha will have a changed composition. So chemical composition is dependent on temperature. So composition is dependent on temperature. So composition is not a degree of freedom. Temperature is a degree of freedom. So only 1 degree of freedom. And that is what the Gibbs phase rule also says. Degree of freedom here should be 1 and not 2 as the earlier wrongly constructed diagram had been showing. So I think this was something important and I have been able to explain the things to you. Thanks for watching. Thanks for your time. Thank you so much, students.